Cool. So it says, given the following vector field, find a formula for the divergence of f. And so remember, divergence is a scalar that we can calculate for a vector field where the divergence of f is going to be the nabla operator dot product f. So our little nabla is the 3D vector. And like I said, it's not really so much a vector as it is what you'd call an operator. And the operator is just where you take all the partials with respect to x, y, and z in this case. So if I talk about the nabla dot product f, and f is given by this vector, which has first entry 2xy plus z, second entry x squared plus y, sorry, x squared plus z squared plus 1, and third entry 2yz plus x. Then you know how to take the dot product. You just multiply entry-wise. You know, first entries, second entries, third entries, and then you add them up. But what it looks like to multiply by partial derivatives is we're actually just going to take the partial derivative with respect to x of 2xy plus z. And then we're going to add to it the partial derivative of, with respect to y of x squared plus z squared plus 1. We're going to add to it the partial derivative with respect to z of 2yz plus x. So that's what it means to take the divergence of a vector field. Okay, so what is the partial with respect to x of this stuff? 2y. What is the partial with respect to y of all of that stuff? 0. And then what's the partial with respect to z of this stuff? 2y. So the divergence of this vector field is 4y. The divergence only cares about what the y coordinate is. Okay, makes sense? Any questions? No? All right. Next example is the exact same vector field, so you don't have to write it twice. But this time we're going to try to find a formula for the curl of f. And the curl is where we take that little nabla operator and cross product f. So this curl is going to be the determinant of the matrix, where little I, j, and k are my standard unit vectors. And the second row of this kind of matrix thing is going to be the partial with respect to x, the partial with respect to y, and the partial with respect to z. And then the last row of this sort of Frankenstein matrix thing is going to be 2xy plus c, x squared plus z squared plus 1, and then lastly 2yz plus x. And I'm kind of being weird about it and not calling this a matrix because the first row of this matrix is all vectors, and that's not normal for the entries in a matrix. And the second row of this matrix is all operators, which is again not normal for a matrix. And then only the last row actually contains expressions. So not technically a matrix, but we're still going to pretend to take the determinant because that's how the cross product works, if you remember back from a few months ago now. So this is going to be I times the partial with respect to y of 2yz plus x minus the partial with respect to z of x squared plus z squared plus 1. Okay, minus j times the partial with respect to x of 2yz plus x minus the partial with respect to z of 2xy plus z plus k times the partial with respect to x of x squared plus z squared plus 1 minus the partial with respect to y of 2xy plus z. And so this curl is going to end up being itself a vector field. And it's going to be equal to, like I said, a vector. I can write this as a vector. So the first entry is going to be what I get for I, my I coefficient. And so what's the partial with respect to y of 2yz plus x? What's this part? 2z. Yeah. That's going to be 2z minus, what is the partial with respect to z of this stuff? 2z. Very good. And the next part, my j, is going to be my second entry in this vector. So what's the partial with respect to x of 2yz plus x? 1. And then minus, well, I guess it's supposed to be the whole thing negative, right? Because this is my j component. But minus, what's the partial with respect to z of 2xy plus z? 1. Okay. And then for this last component of my vector, my last entry, what is the partial with respect to x of x squared plus z squared plus 1? 2x. And then minus, what's the partial with respect to y of this stuff? 2x. Okay. So this curl of this vector field is the vector 0, 0, 0. And so like your little sheet says, this vector field is what you might call irrotational because the curl is the 0 vector everywhere across the whole vector field. There's no curl happening. And that means this vector field is what? I said yesterday there's a special kind of vector field that's kind of neat. And conservative, yeah. This vector field is conservative if the curl is the 0 vector. This is a conservative vector field because it's irrotational. Okay. Questions about that example? Does it make sense how to take the curl? Okay. You can compute curls. Okay, so this might be redundant. Oh no, it's kind of not redundant, but it says, given the following vector field, it's the same one. Determine whether the vector field is conservative, and we just said yes, the curl was the 0 vector, and so that is definitely a conservative vector field. And since it is, we're going to find the potential field. Okay. So I'm going to just go ahead and, well, I'm going to call the potential field capital F. I think your book actually uses the reverse notation. I'll maybe talk about that in a minute, but we're going to name it capital F for the potential field. And the way it works for a conservative vector field is that the vector field, the conservative vector field is, oops, the gradient of the potential field. And remember, the potential field is a scalar field. And the example, I think the best example, is like the gravitational force field, like for example, in the solar system, is a three-dimensional space full of vectors that point in the direction that the force of gravity would be pushing you. But we can also talk about gravitational potential energy and how much gravitational potential energy you have at any point in space. That would be the potential field of the gravitational vector field. So gravity is a conservative field. Okay, so if you wanted to find this, though, if you actually wanted to find what that potential field is, then yeah, we're going to integrate, yeah. So that means that 2xy plus z is the partial with respect to x of the potential field, right? So that's what it would mean to take the gradient. And it would mean that the next one is, I can't remember, x squared plus z squared plus 1. That is the partial with respect to y of my potential field. And then 2yz plus x. That must be the partial with respect to z of my potential field. Okay. And again, the reason I'm writing these equations is because I'm saying that my conservative vector field that has these entries is the gradient of my potential field, which I'm calling capital F. Okay. So now, if I wanted to find what this capital F is, what I'm going to do is take the antiderivative with respect to x, and then take the antiderivative of this thing with respect to y, and then take the antiderivative of this thing with respect to z, and then we'll just see what we get. So, of this thing, and when I take the antiderivative with respect to x, what is that antiderivative going to be? X squared y plus, xz. And then plus, plus, I'll call it g. I'll call it plus g1 of y and z. So I don't know what the function g1 is, but there could be some function of only the variables y and z there. And then whenever I took the partial derivative with respect to x, any function that's only a function of y and z would disappear. And so I wouldn't see it pop up in this expression. Okay. So then for the next one, what would happen if I took the antiderivative with respect to y of that expression here? It would be x squared y plus, yz squared plus y. And then now I'm going to say this, and this is also important. I'm going to call it g2, and g2 is going to be a function of only x and z, because there could be a function that only depends on x and z, and whenever I took the partial derivative with respect to y, it would disappear and I wouldn't find it. Okay, the last thing is I'm going to take the antiderivative of this expression with respect to z, and this is going to be yz squared plus xz plus some g3 function, which is only a function of x and y. So our last job here is we're going to compare these three different expressions that I got for my potential field, right? I'm saying all three of these on the right, all three of those are valid potential fields. And by being a good detective, you can find out what G1, G2, and G3 are. So I see x squared y. I see that appear there and there. But I don't see it appear in this last expression. And so that means that G3 of x and y has to have a term that looks like x squared y. But that's fine, because x squared y is only a function of x and y. What do we have next? I've got xz here, and I've got xz here, but I don't have it in the middle. So maybe g2, which is a function of only x and z, has a term that looks like x times z. And then in this third expression, I've got yz squared, and in the middle expression I have yz squared, but I don't see that in the first expression. So maybe g1, which is only a function of y and z, that must have a term that looks like yz squared. Okay, in the middle expression I also have a little y, and that y doesn't appear anywhere, but that's fine because I could add it to g1 and I could add it to g3. And now I've accounted for everything that I found from taking the antiderivative. And now I know what G1, G2, and G3 are. And if I plug all those things in for G1, G2, and G3, then those three expressions are going to match. And so all three of those are now exactly the same, and they represent what my potential field will be. Okay? So at the end of this, I can write my potential field is equal to, let's just look at the last one and say it's going to be yz squared plus xz plus x squared y plus y. And by the way, I can also add some little constant, right? I can add some little constant, and whenever I take the partial derivative with x, y, or z, the constant goes away. And so if I wanted to be super duper careful, I could add plus c plus c plus c to all those, but that's the idea. Does this make sense, what we just did? And if you wanted to check your work, you could just take the gradient of this potential field and make sure you got back what our original vector field was.